example of electromagnetic induction that helps us illustrate conservation of energy. The scenario we're considering is I have a conductor that is attached to two conducting rails, and the conductor is going to slide to the right at a constant velocity. And it's in a region where there's a uniform magnetic field directed into the plane of the page. So I'm going to go through and answer several different questions to build up to the point that we have expressions for the rate that energy is being transferred to the sliding conductor. Compare that rate that energy is transferred to the rate that energy is transferred through Joule heating in the circuit. The first thing we want to think about is what's the direction of the induced current? And as we're starting off, hopefully you realize there's not a complete circuit. There is no induced current. So let me modify this. By making it into a complete circuit. So now I have a resistor of resistance R to complete a loop. Now I have a complete circuit, and now I can have an induced current. There would be motional EMF and charge separation across this conductor. That's all good and well, but it couldn't flow as a continuous current, and that couldn't make an induced magnetic field. All right. So now let's think about what the direction of the induced current is. As this slider moves to the right, the area of the loop is getting larger with time, and so the magnetic flux is getting larger. The magnetic flux getting larger with time means that from Lenz's law, to oppose the change in magnetic flux, I'm going to have a magnetic field that has the opposite polarity as this applied field. So that is into the plane of the page. So my induced magnetic field is coming out of the plane of the page. And to get a magnetic field coming out of the plane of the page, I have an induced current, and the EMF from Faraday's law of induction is going to be circulating around counterclockwise. All right, so now let's start to construct some expressions. First thing we want to get is what is the magnetic flux as a function of time for our loop. So the flux of the magnetic field through the loop, let's give this some parameters. Let's call that width W, and let's call that L. So the magnetic flux as a function of time, well, the magnetic field is uniform, so it's just going to be the magnitude of our applied field. One dimension is constant that goes into the area. The other is this length. That length is going to be the speed that this slides along the rails times the time that's been moving. All right, then let's use Faraday's law of induction. What is the magnitude of our induced EMF? So we're using Lenz's law to get the direction of the induced magnetic field and then the induced current and EMF that cause the induced magnetic field. And we're just using Faraday's law to get the magnitude. We're ignoring the minus sign in Faraday's law and the sign in the rate of change of flux. All right, well, we have what the flux is. So we just found it. And the delta T in the numerator cancels out delta T in the denominator. So our magnetic flux, rate of change with time, is going to give us the induced EMF. That will be magnitude of the magnetic field, the width of the loop, times the speed. And it's this speed that is causing the area of the loop to change, which causes the flux to change. You might recognize this. This looks just like our motional EMF. All right, so we have the magnitude of the induced EMF. The next question is, what is the induced current? Well, we have Ohm's law. So the induced current is going to equal the EMF over the resistance. So far we have magnetic field strength times the width times the speed over the resistance in the loop, R. Next question we want to address, what force are you going to need to exert on this wire so it keeps sliding at a constant velocity? Well, I'm going to have to exert a force that is just as strong as the magnetic force on the induced current. So the magnetic force on the induced current is going to be magnitude of the induced current times that length, which is our width, times magnetic field strength. And fill in what the induced current is, and we're going to have B squared, width squared, speed over the resistance. That magnetic force, we work it out, it's going to be a current that's flowing up the page. So IL is pointing, well, IW is pointing up, applied magnetic field is in, so the magnetic force on this slider is to the left. So you are going to push with a force just as strong, B squared, W squared, V over R to the right. That will keep the net force on this slider 0, so it can move at a constant velocity. Okay, Next question we want to address is how much work are you doing to push the slider? So the work you do is going to be the force you exert dotted in to the displacement that the slider undergoes. Those are parallel to one another, so we can just write that as the dot product is your force times the displacement, and we're going to rewrite that as your force times V delta T. So V delta T is replacing the displacement delta X. We just found what force you have to push with, so let's put that in, and we are at B squared W squared. Now we'll be at V squared over R, because we picked up another power of V, times delta T. We're going to look at the power that you are exerting to push the slider at a constant velocity. So that's what rate do you do work at? So the power you are exerting and we just found that. B squared W squared V squared over R. I have a delta T and a delta T in the numerator, so that cancels out. So the rate that you have to do work is going to be B squared W squared V squared over R. And now let's close the loop and see the logic of it. What power is dissipated in the resistor? That power is going to be the induced current squared times the resistance. We have just previously found an expression for the induced current. We square that, we're going to have B squared W squared V squared over R squared times R. So we cancel out one power of the resistance, and energy is going to be consumed as heat in the resistor at a rate B squared W squared V squared over R. And those are precisely the same as they have to be. Every bit of work that you do pushing against the magnetic force to keep the slider moving at a constant velocity is being consumed as heat in the resistor through Joule heating. And this is showing you how mechanical energy, by forces doing mechanical work, becomes electrical energy, also doing work and transferring just from one precisely the same rate into the other.